Right, today we're going to be looking at the heating effect of an electric current, and so we're going to be starting work with circuits. In our first video, we will learn the names and symbols of the main circuit components, and you will differentiate between series and parallel circuits. And finally, you'll be investigating what happens to current and voltage in both series and parallel circuits. Firstly, we're going to review the main quantities that we consider in a circuit. Throughout the entire section, we're going to be talking about current, which is measured in amps, voltage, which is measured in volts, and lastly, a quantity called resistance, which is measured in ohms. Now, you've met the current before, because current is the number of electrons, or charges, per second. It's the rate of flow of charge. Voltage is the push on the electron. It's the amount of energy that it's carrying. The last quantity is resistance. Resistance is how difficult it is for the current to flow. It expresses the difficulty of getting the current through a certain component. The more resistance a component offers, or a section of a circuit has, the more difficult it is for the current to flow through it. And this affects the current in the whole circuit. All circuits need one source of energy. The source of energy in a circuit is often called a cell. This is a single component that transfers chemical energy to electrical energy. When cells are connected together, they're called batteries. Although in everyday language a cell is almost always called a battery, the longer line represents the positive terminal of a cell. So, this is how we would draw a cell, and this is how we would draw a battery. So when we have one of these, we're usually referring to a single one of these, and when we have a picture like this one, we're talking about a number of different ones in a row. The plus represents the plus terminal, which would attract the negatives to it, and the negative, the smaller arm, would then be a source of repulsion for the negative charges. A circuit always has a number of components in it, apart from the battery, and you're going to come across most of these in the next few weeks. Lamps, you know what a lamp is, they tend to be drawn like this. We have switches, which open and close. Voltmeters, which are the instruments that measure voltage. We have ammeters that measure current. And then we have something called a resistor. A resistor is simply an object that you're putting in the circuit which is going to slow the current down. And you can have a fixed resistor, that means one that will have just a constant effect, or a variable resistor which will allow you to vary the effect on the current, and therefore you'll be able to change the current. A potentiometer we'll come back to later, but it's simply a more complex version of a variable resistor. Then we have some light-dependent resistors. These are fun. These are resistors that change depending on how bright the light shining on it is. And along with the thermistor, this is a resistor which will change its resistance when the temperature changes. These are kind of fun because they allow you to change what's going on in the circuit depending on what's going on outside, environmentally. Transformers will come to in topic 12. We don't need to worry about that. Diodes and capacitors as well. These we'll save this fun for later. Now, in order for a circuit to be complete and to work, it must have a power supply which is switched on, and it must have a complete path. So the current must have a complete path to flow around. It doesn't mean that the entire circuit has to be connected. As long as there is a loop that the current can flow in, then the circuit will work, even if it's just a part of it. Now, this brings us to the idea of a series and a parallel circuit. In a series circuit, all the components are connected up in series, one after the other. In this example, we have two ammeters, and we've got a power supply connected to an ammeter. The ammeter is then connected to the light bulb, and then the light bulb is connected to the second ammeter. And then the ammeter closes the circuit. If I was to open this circuit in any here, right, then it would stop working. Now, A parallel circuit is a circuit which offers branches and has a number of loops available. So as you can see here, this is a parallel circuit because we have the battery connected to one bulb, but there is a branch, which means that the battery is also connected to a second bulb. Now, the current that flows through here does not necessarily or does not have to flow through this cell here. The flow of the current would be to the first bulb and then back to the battery. And then you could have an outside loop here and then back to the battery. So what we've got here are two possible routes for the current to flow in, whereas this one only has one. Having said that, it should be easy to understand why this is not a very versatile circuit, because if the circuit breaks anywhere along here, the whole circuit is affected. If this bulb breaks, the rest of the circuit can still function. And that ultimately is the advantage of a parallel circuit. Now in today's lesson, you're going to investigate the current and voltage in series and parallel circuits. Your task looks as follows. You're going to set up initially a current in series. You only have one ammeter, so this picture does not refer to 3 ammeters. It just means that you're going to change the position of the ammeter to position 1, which is between the power supply and the light bulb, position 2, which is between the 2 light bulbs, and position 3, which is between the light bulb and the battery or the power supply again. So what you're going to do is measure in amps the current in those 3 positions and make a generalization about what current does in a series circuit. Remember that current is the rate of flow of electrons. Ultimately, you're going to say in a series circuit, the rate of flow of electrons, what does it do? Ammeters, by the way, are always connected in series. What does that mean? That you will connect basically one terminal, basically all in a row. So you'll connect the power supply to the input of the ammeter, and then the output of the ammeter will go straight to the bulb. So it's actually inside the circuit. All the flow of charge has to go into the ammeter. The next thing you're going to do is measure voltage in series. Now remember, voltage is the energy that's going in and out of the circuit. The power supply is where the energy is coming into the circuit. So if you were to measure the voltage across here, you would be measuring the EMF. That's the energy that's coming in to the circuit per unit charge. For this experiment, however, you're going to focus on the energy that's leaving the circuit. We refer to the energy leaving the circuit as the potential difference, or the PD. Now, voltmeters, the instruments that you're going to be using, are added to the circuit in an interesting way. They're not part of the circuit. They're parallel to the components. That means your voltmeter does not get plugged straight into the circuit. You use the terminals of the voltmeter to connect to either side of your component. So what this voltmeter is going to do is it's going to compare the charge coming into the light bulb with the charge coming out of the light bulb. So you connect it in parallel on either side. You're going to look at the energy leaving the circuit across one cell. You're going to look at the energy leaving the circuit in the second cell. And that would give you an idea of what happens to voltage in series. And then to get an idea of how much voltage there is in total, like what is the total PD, you can do 2 things. You can measure V3, which is the total energy in the cell, or you can measure the EMF. V3 and the EMF should be the same. See if you can think why. So here's a picture of a voltmeter. Now in parallel, what you would do is you would have the terminal of one side of the voltmeter plugged in to a side, the side of one bulb, and then you would take the other terminal and you would plug it into the side of the other bulb, one on either side, yet the circuit itself is unaffected. Good luck with that. At this stage, you should be able to come up with a conclusion for current in series and current in voltage in series as well. So finish off your conclusions for current in series. What are your generalizations? And then secondly, come up with a generalization for voltage in series. Once you've done that, we'll repeat the entire process for parallel circuits. Build initially without an ammeter, just build a parallel circuit, a circuit which is represented by this. Careful with your parallel connection. How are you going to do this? Now, once you have that set up, you can try your ammeter in 3 different positions, or 4 even. You can put your ammeter here before the branch. Then you're going to look at what's happening after the branch here and here. And then you're going to see what happens after the 2 branches come together in your position 4. Which you can see here. Your 4 current positions. Should be able to generalize what's happening to the current as it basically as it moves into these bulbs. I'm trying not to give the game away, so I'm choosing my words carefully. So when the bulb, basically the current through these bulbs, what is the relationship between the current in the battery, for instance, and the current in the bulbs? Once you've done that, do the same with voltage. You're going to get your voltmeter and you're going to connect it up to either side of the power supply. That will give you your EMF. That's the energy coming in. And then have a look at what's happening in each of the bulbs. And so therefore, what's happening to the energy coming out of the circuit. Once you've done that, you can make your 4 generalizations.